Welcome to the Walton Pi. Today we're going to be going over a theorem and then the proof of that theorem to show that there exists a unique minimal completion of a measure. So let's start by writing down the theorem. So let's let xmu be a measure space. Let's let n be the set of all the null sets in our sigma algebra, so the set of all the sets in our sigma algebra M where the measure of that set is 0. And let's let m bar be the collection of all sets of the form F union A, where A comes from our original sigma algebra M, and F is a subset of one of these null sets. Then the theorem tells us that m bar is going to also be a sigma algebra on X, and that there is going to be a unique measure mu bar on X m bar, which extends mu. So let's go through the proof of this theorem. So we're going to start by just writing down all of the premises of the theorem. So xmu is a measure space, n is the collection of null sets, and m bar is going to be exactly what we had it before, where it is a subset of a null set unioned with a set from our original sigma algebra M. So note that by the subadditivity of mu, if we have the collection of the ni's, is a countable collection of null sets, then 0 is less than or equal to the measure of the union of those null sets. Here's where subadditivity comes in. It's less than or equal to the sum of the measures of all of those individual null sets. So we have a countable sum of 0, which is just 0. So that tells us that the measure under mu of the union of all these null sets is 0, and the union of all of these null sets is also going to in fact be an element of script n, or the collection of all of our null sets. So now we're going to move on to showing that m bar is a sigma algebra. So there's a few things we have to show, and we're going to go through each of them. So first, let's let pi be a countable collection of elements in our new proposed sigma algebra m bar. For each of the i's in the natural numbers, we're going to choose an ai and then fi. So ai comes from our original sigma algebra M, and fi is a subset of one of our null sets, where we can be able to write pi as ai union fi. Then the union of all of those pi's is the union of the ai's with the fi's, which is the union of the ai's unioned with the union of the fi's. This is a common thing that we'll see a couple times throughout this proof. And so since the union of the fi's, that's a subset of the union of the ei's, which is one of our null sets, the union of our pi's is in our m bar, because the union of the ai's, that's also going to be in our original M. So now we're going to show that m bar is closed under complements. So to that end, let's just pick something that's in m bar, and we are going to show that x minus e is going to also be in m bar. So then there's going to exist an A in our original M and F a subset of a null set, where E is a union F. So note that the measure of n minus A is going to be 0, because that's a subset of a null set. So E can be written as A union F minus A. And note that that is also a form where we have A, that's an element of our original sigma algebra M, and then F minus A, that's a subset of a null set. So that tells us that this is also a sufficient way to break up E to show that E is in M bar. Now the reason we're doing this is A and F bar, A and F minus A, both of those don't intersect with each other. So that tells us that without loss of generality, we can just assume that F intersect A and N intersect A are empty. So we're assuming that we are writing E as the union of two things that have no overlap, because that just makes the proof a little bit easier. This is a common technique in analysis proofs when overlap would be a little bit tricky, so keep this in mind in future proofs that you might come across. So we can be able to write x minus e as x minus A union F, which is x minus the union of A and N, unioned together with the set N minus F. This is a little bit of De Morgan's laws and just element chasing. So go ahead and draw out like a Venn diagram to try and figure out what's going on. And you can notice that this is actually going to be true. I'm just not going to go through those De Morgan laws here. So note that x minus a union n, that's an element of our original sigma algebra M, because a, n, and x, all of those came from M. And then n minus f, that's a subset of n, which is one of our null sets. So that tells us that x minus e is an element of M bar, so M bar is going to be closed under complements. Now we're going to show that M bar is closed under countable unions. So to that end, we're going to let each of the EI's be in our M bar for I in the natural numbers. And then again, there's going to be AI's and FI's, where EI can be written as AI union FI, where each AI comes from M and each FI is a subset of a null set. So again, without loss of generality, just like the argument we had on the previous slide, we can assume that FI intersect AI is going to be empty, and that the NI intersect AIs are also going to be empty. So then the union of all those EIs is the same as the union of the AI union FIs, which, as we've seen before, is the union of the AIs unioned with the union of the FIs. And then we can note that the union of the AIs, that's an element of our original sigma algebra M, and the union of the FIs, that's a subset of the union of the NIs, which is a null set. And so that tells us that the union of the EIs is an element of M bar. So M bar is going to be closed under countable unions. All of this tells us that M bar is going to be, in fact, a sigma algebra. Now we're going to go and deal with the measure part. So we're now going to show that there's a unique measure mu bar on xm bar which extends mu. So let's start by defining what measure we want it to be, and we're going to then check that this is in fact the unique measure. So we're going to define mu bar to go from m bar to 0 to infinity. Note this can take values of infinity, where mu bar of A union F is equal to mu of A whenever A is an M and F is a subset of N, which is then going to be a null set. Now, this definition is a little bit vague. How do we know that A union F is the only way to write it? We don't. So we have to check that this is a well-defined one, that it does not matter which A we had chosen. So let's go ahead and do that. Let's suppose that we have two different ways of breaking our set up. So A union F, B union G, A and B are in M, and F and G are subsets of null sets. So let's note first that B union G is a subset of B union N prime. N prime is that null set. And so then that tells us that mu of A, by monotonicity, because A is a subset of B union G, which is then a subset of B union N prime, that tells us that by monotonicity, mu of A is less than or equal to mu of B union N prime, which by subadditivity of mu is less than or equal to mu of B plus mu of N prime, which is just mu of B, because mu of N prime is 0. Similarly, we can get mu of B is less than or equal to mu of A union N, which is less than or equal to mu of A plus mu of N, which is equal to mu of A. So this tells us it doesn't matter which A or B we had chosen, they all give us the same answer. So that tells us that mu bar is in fact well defined. Now we're going to note that mu bar of A, that's the same as mu bar of A union the empty set, which is equal to mu of A for all A and M. So that means it agrees on M itself. So we currently have it is a function which extends mu. We need to now show it is a measure, and then show that that measure is in fact unique. So let's go and figure out, is this going to be a measure? So let's start by letting PI be a countable collection of elements in our M bar sigma algebra, where the PI's and PAJ's don't ever intersect. So it's a disjoint countable collection. For each I in the natural numbers, we're going to fix AI and FI. We've seen this before, so that PI is AI union FI. Then the union of the PI's is the union of the AI's unioned with the union of the FI's. The union of the AI's is an M, the union of the FI's is going to be a subset of a null set. So there we go, the union of all of those is going to be there. But now we're going to go and look at what is the measure. So the mu bar measure of the union of the PI's, well, that's the mu bar measure of the union of the AI's together with the union of the FI's. Well, by our definition of mu bar, this is just mu of the union of the AI's, which these are disjoint, pairwise disjoint a countable collection, so we're able to break this up by the countable additivity of measures. So this is the sum of the mu of AIs, which is the sum of the mu bar of the PIs. So there we go. This shows us that we have countable additivity, and also the empty set behaves nicely, so it is going to be a measure. And now to see that it is unique, suppose that gamma is also a measure that extends mu. So then pick some A in M and F a subset of a null set. Gamma of A is less than or equal to gamma of A union F, which is less than or equal to gamma of A plus the gamma of F. This is using monotonicity and subadditivity again, which is then less than or equal to gamma of A plus gamma of N. This is by monotonicity, which is gamma of A plus 0. Okay, so that means all of those less than or equals can get replaced with equalities because of a basically the squeeze theorem, showing that these inequalities have squeezed everything in the middle to be equal. But then gamma of A is equal to mu of A, which is equal to mu bar of A union F. So that tells us that gamma of A union F is the same as the mu bar of A union F, which tells us that gamma is in fact equal to mu bar everywhere. So this shows that it is in fact unique. I hope this was helpful. If it was, please like and subscribe, check out some of my other videos, and if there's other topics you want me to discuss, please leave them in the comment section down below. I do go through and read them. I can't guarantee a video super fast, but I do read them and do consider those as future video topics. I hope you have a great rest of your day, and good luck with all of your math.